Back in the early 70s, engine modifications and early type emission controls left a lot to be desired from the fuel economy and performance standpoint. Electronic ignition, improved engine modifications, and more precise emission controls introduced in the mid-70s, along with downsized cars, resulted in improved fuel economy, but drivability and performance still suffered. Basically because air-fuel mixtures had to be kept very lean to help assure reduced emissions.
Beginning in the late 70s and gaining more momentum in the 80s, manufacturers began introducing electronic control of timing, fuel metering, and various other systems. This has enabled the manufacturers to put performance back into driving and at the same time meet or exceed the emissions and fuel economy standards.
In this AutoKnow program, we will discuss basic operation of these systems. We'll review some quick test methods to determine system operation, and we'll illustrate some typical methods of accessing the diagnostic codes.
The computer or electronic control module, with the assistance of various input sensors, not only provides basic timing and fuel metering control, but it constantly fine-tunes both systems for optimum performance, fuel economy, and reduced emissions. In addition, on many vehicles, a self-diagnostic system alerts the driver when a problem occurs that may or will affect operation. It also quickly leads the mechanic to the probable cause through a diagnostic output connection.
Let's have a look at some of the system components and how they work together. Sensors are actually transducers, or devices that convert various forms of energy, such as mechanical, heat, pressure, and chemical, into electrical signals. Some typical mechanical sensors being used are distributor shaft position and speed, and throttle shaft position sensors.
Typical heat sensors are engine temperature and intake manifold air temperature. Pressure sensors such as manifold vacuum and barometric pressure are also used. The oxygen or O2 sensor is a chemical energy sensor. It generates a voltage based on the difference between oxygen content of both atmospheric air and exhaust gases.
Many systems actually sense 10 to 15 or more different operating conditions, all providing input to the computer. The computer processes these signals along with self-contained information called Programmable Read-Only Memory, or PROM, and makes numerous lightning-fast calculations. It then sends output electrical signals to some devices which can convert electrical energy back to mechanical energy as a means to regulate air, fuel, and vacuum.
For example, idle speed control, electric fuel pump operation, fuel mixture valve control, fuel injector control, or air injection system control. In the case of electronic timing control, the computer output electrical signals are actually controlling the operation of another electronic circuit, the ignition module.
Many systems provide 10 to 15 or more output signals to control various other functions, such as air injection, transmission shifting, turbo wastegate, cooling fan, and canister purge, to mention a few.
The diagnostic section of the computer is almost a mini-computer itself. First, it monitors all input, output, and many internal computer circuits for proper operation. These could be considered input signals. Second, it detects and remembers what circuits are not operating properly. And third, it provides at least 3 output signals. For example, operation of a check engine warning light on many vehicles to alert the driver of a possible problem. Next, it will release the detected faults from memory in various ways. And also, in many cases, it will advise the ECM of the particular fault.
The ECM can often initiate a secondary mode of operation or corrective action, which may prevent serious engine damage and yet allow vehicle operation, even though performance may be reduced somewhat. How does the driver or a mechanic know where there is a fault in the system? On some cars, the only indication of a problem or fault would be poor performance or fuel economy. However, most manufacturers are utilizing dash indicator messages such as check engine, power loss, low power, or service engine.
In some cases, the light will only operate while a problem exists. In other cases, it remains on temporarily for a predetermined number of starts after an intermittent or soft fault, but will be on continuously for hard faults. Yet in others, the light remains on until the problem, be it intermittent or permanent, is repaired. Quick testing begins, as usual, by talking to the customer. Listen to his description of the problem, and of course, test drive the vehicle with the customer if at all possible, even if the check engine light is on or was on. If there is a performance problem, then first check out the items not monitored or controlled by the computer system. These include the ignition system, other than timing control on some, the thermostatic air cleaner, the PCV system, carburetor linkage and circuits other than those electronically controlled, vacuum leaks, and the battery and charging system. Conventional tune-up service will usually take care of these problems, but be sure to refer to the appropriate shop manual for proper procedures and specifications. If the check engine light or other type of message light is on, or the customer advises that it was on for a period of time, then the computer has detected a fault, which will likely be stored in the computer memory. To release the service codes from memory, each manufacturer has a specific procedure that must be followed. For example, on this 85 GM Cavalier, a simple jumper connection with half a paperclip or a simple special tool is inserted into a special diagnostic socket under the dash. With the key on and the engine not running, the light first flashes once, then twice,